Thank you very much. Yeah, my name is Matthias Steg, and in the next couple of minutes, I want to talk about the security of wireless desktop sets, wireless mice, and wireless keyboards. So, yeah, a few words about me. I work as an IT security consultant for a company called SYS, and yeah, it still pays the rent. I'm interested in information security since my early days. And I still have fun doing this. I did this research together with my colleague Gerhard Klostermeier. He couldn't be here today. He's also very interested in information security, and we did this research, as I said before, together over the last couple of months, actually. So the agenda for this talk, we have a few points. At first, I want to shortly introduce you to the used technology I will gonna talk about. Then, I will mention the previous work of other researchers. Our research is actually based on. Then I will give a short overview of our research, talk about the attack surface and attack scenarios concerning wireless desktop sets, wireless mice, wireless keyboards. Then the interesting part is the found security vulnerabilities. There will hopefully be also live demos. I have one set up here, I hope it works. And of course there's conclusion and recommendation, and if we have still time, some Q&A. Okay, so what I was going to talk about is wireless desktop sets. You can see here on the upper side of the picture, wireless desktop sets is just a combination of a wireless keyboard, a wireless mouse, and a USB dongle that is working as a receiver and gets connected to a PC. On the lower side of the picture, you can see some of the devices we used for our research purposes. So I, for example, used a HackerF1 software-defined radio. Later on, we used a Crazy Radio PA. It's a specific device using the same technology as our target devices. And nowadays, you can also do these kinds of attacks I show you using low-cost devices like a Logitech unifying receiver, thanks to the Still networks, because I found out that that you can actually reprogram these devices. They cost about 16 to 20 euros, and you can do all the kinds of attacks you will see later on using such a unifying receiver. Okay, so how do wireless keyboards actually work? What I'm talking about? Well, you have wireless devices, mouse and keyboard, and they're just sending keystrokes in the case of the keyboard to a USB dongle, and in the case of the mouse actions like mouse movements or mouse clicks. The communication actually is not unidirectional, but goes in both directions. There are no acknowledgements, but they are not that important here. Okay, and our research actually is based on the research of other researchers, as mentioned before. Back in 2009 and 2010, there was Kikoriki in version 1 and version 2. This project targeted, for example, Microsoft wireless desktop sets, and the guys doing it from Dreamlab Technologies also reverse engineered the proprietary encryption of the wireless keyboard, and they were able to attack devices back then. In 2011, Travis Goodspeed published a paper or a blog article about sniffing using a specific kind of transceiver, namely the NRF24. And last year, as part of the NSA playset, Semicamcar released the Key Sweeper. It's an improvement to the research done by the Kikoriki team, actually. And in February this year, Bastille Networks released several vulnerabilities they called Mousecheck. And we actually did something the same. So our research started way back in April 2015. It started as a customer project where we had a look at 3 specific IES encrypted wireless desktop sets. But we only had limited time, and we were not that content with the results, and we thought there must be more to it. So we started a research project over the last few months. It was a very fragmented research project because there were always more important things to do, like earning money. Okay, on this picture you can see the 5 devices we had a look at. It was one device from Cherry, one from Microsoft, Fujitsu, Logitech, and also Perix. We have chosen those devices by the project we initially did, and then we just did a research on Amazon, Germany, to see what can we find if we type wireless desktop set in AES, and these were devices we could simply buy there. Okay, so our test methodology was 3-step actually. First we did a simple hardware analysis, so we opened up the devices, we stared at the printed circuit boards, identified chips, did a lot of reading documentations, and then we tried to find interesting test points, for example for SPI, and we were also soldering some wires to some interesting test points. Next, we did firmware analysis, so we were capable to actually extract firmware of some of the devices under test, and we loaded the dumped firmware. It was actually 8051 code of the microcontrollers of the specific transceiver to IDA and analyzed it. We started disassemblies, we did some more reading of fine documentation, we checked the Nordic Semiconductor's software development kit, which was very useful, and we read some more code, wrote some sample code, and analyzed this, just to get a better understanding of how these devices actually work. And lastly, we also did radio-based analysis, because these devices are wireless, and this is the most interesting part. How do they work actually? And what I personally did, at first I watched Mike Osmond's SDR tutorials. This was actually my first project working with a software-defined radio, and I learned a lot. I did some more reading of documentation, browsed the web, because we found out that these NRF24 devices are very popular in the maker scene, at least the transmitters and receivers, not the transceiver system-on-a-chip devices, but many people are using these transmitters for different stuff. And then we also got started with GNU Radio and GNU Radio Companion. We wrote some Python scripts and analyzed the data communication using readily available tools from other projects. And later on, we changed our tool set to this of Bastille Networks in February this year, because it was just superior to that one we have used up to then. And in this table, you can see the transceivers we were able to identify. And 4 of the 5 devices, as you can see, are using the Nordic Semiconductor transceiver NRF24 kind. And we focused our research on these devices. So Fujitsu is still a work in progress. It's another technology, and we were just able to identify one vulnerability in there. I will show you later on. Okay, on this slide I've just compiled some information about documentation. It's just very important, if you haven't done such a project before, to read all the stuff, to just know what are you looking at, and it is also helpful to do some research about available tools, because it saves a lot of time, actually. Okay, and on the next couple of slides, I've just put some excerpts from the data sheet. So this was actually the device in this package that we were dealing with, the NRF24, different versions in the keyboard and in the USB dongle. And the interesting pins for us were, of course, SPI, because via this serial interface we were able to dump the firmware, and we could also reprogram some of the devices. This was the first interesting finding, because the Nordic Semiconductor transceivers actually have a read-back protection, but 3 of the 4 manufacturers just don't use this feature. And so you just have to find the correct test points, and you can modify the device, or you can just dump the firmware for further analysis. And when it comes to data memory, it is divided in 2 parts, the non-volatile data. Not all memory is accessible externally via SPI. So, for example, for the Cherry keyboard, we had to write our own firmware to extract all the data that was on the devices. So it was not all externally addressable, as you can see here. On this slide, you can see some information about the so-called enhanced shock burst protocol that is used for the radio communication. We were mainly interested in the payload and not on the other stuff. Yeah, but if you have a look at these devices and do an analysis, you have to know how it actually works. What is the preamble, the address configuration fields, control fields, checksums, all that stuff. But it's all well documented. And what's also interesting, it's shown on the lower part, is that the Nordic Semiconductor transceiver has support for hardware AES encryption, and it's actually used by the firmware we had a look at. So on this slide, you can see a Microsoft keyboard, or actually a PCB. And what's nice from Microsoft is they have labeled all the interesting test points for us, so we do not have to search them by our own. So you can see, yeah, we have all the SPI things, MISO, MOSI, chip select, a clock, and we also have the reset and proc test points there. So it was very easy to analyze this one. And yeah, that's an example setup. We used just a bus pirate. That's a Cherry keyboard, wired soldered the correct wires on the correct test points, and then you just can modify and read the things. Okay, and we did not only have a look at the keyboards, but also at the dongles. So my colleague Alexander Strassheim did this one. Yeah, and so we were also able to directly read the dongles in this way, using custom-made breakout boards. Okay. Yeah, and concerning firmware analysis, what we did, as I mentioned earlier, we just loaded it to IDA Pro, read the Nordic Semiconductor SDK several times, and by having the SDK, it was rather easy to identify the interesting spots concerning encryption, for example, so we could annotate the code section we were mainly interested in. Yeah, and concerning radio-based analysis, we started with GNU Radio and GNU Radio Companion, and yeah, some self-made scripts just to analyze what was going on over the air using the enhanced shock burst communication protocol. Yeah, and this is just an example of our first tries using the NRF24 decoder. We modified a little bit, and here we're able to see the encrypted traffic and some more information concerning addresses, PIDs, acknowledgement, stuff like that. So this is just a raw communication. Yeah, and in February this year, we changed our tool set a little bit because Bastille released their own tool set they used for identifying the mouse check vulnerabilities, and their tool set was just superior to ours. So we also bought a crazy radio that's actually a remote control for a quadrocopter. And we used Bastille's NRF research firmware and some of their tools, and all the tools we have developed so far are based on this tool set. Yeah, and of course there were different problems during our research project. What I've learned personally is that software-defined radio really has a steep learning curve. So reproducing some things at the start is really easy, but later on when there are some issues, you really have to dig deep and find out what's going wrong and where the error is. But it's fun, so I will continue doing SDR analysis in the future. Yeah, and some things just were more difficult than we first thought. For example, simple replay attacks, because there is channel hopping, there are timing issues, signal strength issues, stuff like that. And what we also found out is that correctly identifying chips is an art in itself, because we overlooked at first that there are also one-time programmable versions of some of the chips. Yeah, so we bricked one Microsoft device. Yeah, that was not our intention. Yeah, and the other 2 points are rather general. If you have a development kit or board where you can just play around without breaking and damaging it, you can save a lot of time, and having a proper tool set makes a huge difference. Okay, so what actually is the attack surface and what are attack scenarios concerning wireless desktop sets? In our opinion, there are two attack categories, one with physical access to the devices and one where you remotely attack the devices over the air using radio signals. Concerning physical access, what could you possibly do as an attacker? You can, of course, extract firmware, manipulate firmware, extract cryptographic keys, and manipulate them. Concerning attacks over the air, what can you do? You can exploit unencrypted and unauthenticated data communication. You can perform replay attacks. If there's no protection, you can maybe perform keystroke injection attacks, and you can also try to decrypt encrypted data communication. So all the devices we looked at were encrypted, so we only had a look at AES encrypted wireless desktop sets. Yeah, and here are the five security vulnerabilities we found. Actually, they are only 4 because replay attack is listed there twice. But what we found is that some devices just have an insufficient protection of code, namely firmware, and data, cryptographic keys. So we were simply able to read and also write this sensitive data, as seen before using SPI. Then the second vulnerability we found was unencrypted and unauthenticated data communication. We found this one in all the mice we have tested. So only the keyboards are actually encrypted. All the mice are unencrypted. The next vulnerability was missing protection against replay attacks. So most of the devices had no protection at all against replay attacks, and the Microsoft keyboard had some kind of protection, so that's point 4, insufficient protection against replay attacks. But there is still an attack window you can actually exploit. And the last vulnerability is cryptographic issues that allowed for other attacks, as we will see later on. Okay, so the first vulnerability, insufficient protection of code and data. It's a rather obvious one, so I will rush to the slides. Here you can see sample firmware we used to extract the so-called extended NV flash memory from the Cherry keyboard, because in this way we were able to also get access to the memory that is not externally addressable via SPI. And the Cherry keyboard, for example, stores the AES key in there. Yeah. So you at first have to reprogram a Cherry keyboard or a Cherry dongle in order to actually get to the AES key. In this case, concerning the other devices, for example, Perix or Microsoft, you can just connect to the correct test points for SPI and read the AES key from the device. Yeah, and here's an example of 2 dumps from the Cherry dongle and the Cherry keyboard, and as you can see, we have found the same 16-byte value in the dongle flash memory and in the Cherry flash memory, and this is the actual key that is used. Yeah. So, embedded flash memory of several devices can be read and written. Concerning nRF24 transceivers, there is a protection feature, but it's not used by every manufacturer. So it is rather easy to raise the bar for an attacker having physical access if this feature was used in the manufacturing process. And what we also found out is that it's also possible to manipulate one-time programmable flash memory, because you can change a 1 bit to a 0 bit, but not vice versa. So for example, the Microsoft keyboard uses a one-time programmable version of the transceiver, but you can still modify the key or modify the firmware in a limited way. Yeah, and what's also important is that some wireless keyboards, for example, Microsoft, is paired at the factory. So you have no chance as an end user to actually change the cryptographic keys. You just have to trust Microsoft in this way. We are still working on a software where you are able, exploiting the SPI access, to change the cryptographic keys if you don't trust Microsoft, but it's still work in progress. Yeah, and concerning the generation of cryptographic keys, none of the manufacturers told us how they actually do it, so it can be simply random, it can be derived from some serial number or I don't know what. So it's a secret, and you have to trust the manufacturers that are actually building these devices. Yeah. And what does it mean? It means that an attacker with physical access can change the cryptographic keys and the firmware, and of course read it. And when I hear this, I always have to think of this picture that was released, I think, 3 years ago. Yeah. So anybody who has access to the device for a couple of minutes, it depends on the device, so 5 to 10 minutes, can extract the AES keys, or it can actually manipulate the firmware. And here you can think of some specific keylogger scenarios. For example, yeah, where you just extract the keys and then you're sitting in the building on the opposite side of the street or on another floor and just sniffing the radio communication for a couple of weeks, and you're able to decrypt all the traffic somebody is generating using these devices. Okay, so the next vulnerability and attack that is possible are so-called mouse spoofing attacks, because, yeah, as mentioned earlier, the communication of the mice is unencrypted and unauthenticated. So the receiver cannot decide if it's authentic or not, and so you can just spoof devices and do whatever you want. Okay, so I will show you a small demo video. Hopefully it works. Yeah, because I was challenged by one of my colleagues. He said, yeah, but it's not reliable, exploitable in the real world. So we just developed a small Python software tool called Radioactive Mouse, and I targeted in this proof of concept attack a Windows 7 operating system. And yeah, what I actually did is I opened the virtual on-screen keyboard of the device, and then you can just do virtual key presses there. I sped it up, so it's, the attack is rather slow, at least here in my proof of concept tool. So I think the complete attack has a duration of 3 minutes. You can see a full demo on YouTube. So I think a couple of days ago, or weeks, 2 weeks ago, we put a proof of concept video on YouTube. You can just watch it there. Yeah. And what happens here is just virtual key presses. It's a default Windows attack vector, download and execute via PowerShell. And when the attack is completed, now it's slowed down again, and it presses enter. Now the PowerShell command is executed. And if all goes well, malware just got installed on the system. This kind, it's just a mock-up ransomware. And it's just a demo for remote code execution, wireless unencrypted mouse communication. Okay, so you've seen this here. So the radio communication of all the tested mice was unencrypted and unauthenticated. So if you know the mouse data protocol, you can just spoof arbitrary mouse action, mouse movements, or mouse clicks. And you have control in an unauthorized way over the mouse cursor, mouse pointer. And this is really old news. So back in 2009 and 2010, the people from Dreamlabs, the Kikariki people, they also had this information in their slides, but actually nobody cares, because all people say it's not reliable, exploitable, and it's actually true. Because you need some heuristics to exploit this in the real world, so you have trial and error, educated guesses, but in some cases you have remote code execution. And the heuristics concern the layout of the screen, actually. Then the language settings, you have to know if it's an English keyword or Dvorak or German, for example. You have to know some information about the mouse settings. especially the mouse acceleration that is used, and you have to know where the on-screen keyboard can be found. So it is also changed with Windows 8, 8.1, and 10. But in Windows 8.1 and 10, you have a split-screen keyboard that you can also exploit rather reliably, I'd say. Okay, and these are the defaults I used in my proof of concept. Just the default mouse settings using enhanced pointer precision. There's a default mouse acceleration curve in the registry, and the on-screen keyboard actually has default position and default dimensions if you haven't used it before and moved it and saved it. So I think in most of the cases concerning Windows installations or Windows Office installations in companies, it's rather reliable. And if you're not only targeting one device, but several hundred, one is enough to get access to the company network if the exploit is successful. Yeah, and what I couldn't achieve was pixel-perfect control over the mouse pointer, because there's some more research necessary, because it's not that easy as I have thought at the beginning. Yeah, and actually the mouse movement in Windows is still handled in the kernel, and there is fixed point math involved and mouse acceleration curves. It's more complicated than I actually thought. Yeah, and so the current state is that we are using handcrafted mouse movements that are actually slowed down to avoid some issues concerning mouse acceleration. Yeah, but it works rather reliably, as we've seen in the demo video. Okay, so the next vulnerability, replay attacks. This is also rather obvious, and actually I was surprised that it works on all keyboards. I have also a demo video here, but I will also try to do a live demonstration in combination with another vulnerability later on. So, yes, should be this one. Okay, I'll pause the video for a second. This is just a simple, no? Whoop. Oh, I cannot pause it. Okay, this is just a simple setup. On the left, the laptop, you can see the attacker. There's running GNU Radio. You can see a software-defined radio. And you can see the victim system running Windows 7 that is operated with the vulnerable wireless desktop set. And what I just did is, I recorded the radio communication on a specific channel in this case, and now I simply do a replay of the recorded communication. And as you can see, I can unlock the Windows screen remotely. Yeah, so there's no protection concerning replay attacks. Yeah, and in this case, I attacked the Fujitsu keyboard, and I don't know actually the protocol of the Fujitsu keyboard. So I did this using a black box approach. I just recorded the communication on a specific channel and replayed it. I don't know what is actually going on, but it is easy to reproduce, as you've seen. Okay, this was just a setup. We've seen it in the video. And actually this is the GNU Radio flow graph. It's one of the most simple flow graphs you can get. This can be used for recording and for replaying by activating, deactivating some of the boxes. But that's all it takes to perform replay attacks. And you can do this within a couple of seconds or minutes, actually. It took me 5 minutes to reproduce this on the Fujitsu keyboard. Okay, and we have also written other software tools, simple replay, Python script that uses the newer tool chain, the Crazy Radio PA and the NRF research firmware, and you can just perform replay attacks using this, and you have a better output. Okay, so replay attacks are rather obvious and simple, and all the keyboards we've tested, all 5 are vulnerable to replay attacks. Microsoft was special because It has some kind of protection, and there's a limited attack window because only a specific number of key presses should happen between the recording and the replay. If there are too many key presses on the keyboard, I think it's about 1,000, then the replay doesn't work. But concerning all the other devices, we were able to replay communication we've recorded the day before, and it still worked perfectly. So no protection at all. Yeah, as mentioned before, simple replay attacks can be done without knowing the actual protocol. And yeah, more sophisticated attacks can be done using the other tool set. And what can you do with replay attacks? You can gain unauthorized access to unattended screen lock computers, as shown in the video. And if you can also gain physical access to the USB dongle, the receiver of your victim, you can just steal it and replay the communication on your own device, and then you will get all the clear text key presses in this way. So it's another kind of keylogger scenario, if you want it that way. So if you're able to replace all the wireless desktop sets at a specific facility, as cleaning personnel, no one will notice that you've just replaced the original device, and then you can replay communication you have recorded the weeks or days before, and you can see, for example, passwords. Okay, and now the most interesting one, the keystroke injection attack. And here I will try to do a live demo. But I have to do a quick setup. So I'm just preparing my victim device, but it's only for test purposes. And now I try to do some picture-in-picture hack. Where is it? Okay. So what I have here is a MacBook Pro running Windows 7 as a victim system. So it's not the ideal setup, but I hope that it works. And what I have here is a Cherry keyboard wireless desktop set. The USB dongle is just plugged in to the device. Now I will turn it on and just see if it actually works. So if the device is working, no, I don't want to restart this. Okay, so now this device is connected to my victim system. It's not necessary to see what is actually typed here. It's more important to see that something is happening. Okay. So now I will use a proof of concept tool called Cherry Attack. And now I'll try to live demonstrate two kinds of attack, a combination attack, replay, and keystroke injection. And I hope the demo will support me in this one. Okay, so what I did is I just started the proof of concept tool, and now oh, no, my fault. I missed the most important step, my radio. Without this, well, actually, it should not work. And as you can see here, could not initialize. He also writes it there. So this is the Crazy Radio PA. It costs, I think, including the antenna, 30 euros. And now I'm good to go, I hope. Okay, so here's my attack tool. Now I press some keys here, and as you can see, I found a keyboard. This one is easy because it doesn't do any channel hopping and there are no timing issues. And you can also see there is something going on concerning crypto. And yeah, now I'm ready for the attack. What I will do now is I will try to lock the Windows system to show the first kind of attack. So now you can see the Windows system is locked. And now I just press one button, and now I will record all the data communication of this specific device. Okay. So as you can see, it was successful. The screen was unlocked. Now I will just lock it again and try the replay attack. Ta-da, it works. So that's the first one, the replay attack. So you can simply remotely unlock screen-locked systems. We did not do any range tests, but the people from Bastille did. They were able to do mouse check attacks, I think, up to 100 meters, using some special antennas. Not this one, but yeah, it's possible. Okay, now we have. So this is just a virtual machine. And what I try now is the other kind of attack, the keystroke injection. And let's see if it works. Yeah, you can see something is happening on the device. There's a command shell. It's actually a PowerShell. And if all goes well, there should be some malware popping up. Yeah, it worked. So that's a keystroke injection. So in this combination attack, you can remotely unlock a computer system if you have recorded the password entry at the right time. And afterwards, if the system is unlocked, in an unlocked state, you can simply inject arbitrary keystrokes and do whatever you want. For example, installing malware, as in this case. Okay, so back to the slides. Yeah, so this is another tool, keystroke injector. I showed you actually this one. And this attack works for the Cherry keyboard we've tested, the Perix keyboard, and also the Logitech keyboard. But we did not find a vulnerability concerning Logitech, Bastille did just before us and reported it to Logitech. Yeah, and here you can see an extract from the NRF SDK. And what we found there is that there are differences between two NRF transceiver versions concerning the AES counter mode encryption. And what we found out is that there is not a counter used, but a random value. And then we thought, hey, how are the devices syncing? And the truth is they cannot sync. They're just using random values for the counter mode. And this actually is part of the problem. Yeah, here's just a source code using the pseudo-random number generator for generating these 5-byte random value. Yeah, and concerning the tested Cherry and Perix keyboard, we found out that they're using 128-bit AES encryption in counter mode. The counter generally consists of a nonce, a number used once, and a counter. And we also found out that the nonce of the Cherry keyboard was only null bytes. So we have 11 null bytes and 5 bytes random value for the initialization vector. And by manipulating the Cherry firmware, we were also able to find out some more details concerning the release packets. So by release packet, I mean if we release a key of the keyboard, a specific packet is sent. And we were able to manipulate the firmware, as mentioned before, using SPI and analyze it using IDA Pro. And we were able actually to decrypt all the traffic on the Cherry devices we had. And we found out, hey, if a key release is sent, it's just 11 null bytes. So, and on the bottom of the slides, you can see how counter mode actually works for all block ciphers, in this case also AES. And what we know is all the information I've circled in red. We know the complete initialization vector. The nonce we know because we did a firmware analysis. The counter actually is sent via the radio communication in clear text over the air. The ciphertext is also sending not in clear text, but it's sent over the air in the radio communication protocol. Then we know the plain text, at least of some packets, namely the key release packets. And due to the mode of operation of counter mode, we also know the key stream block. Because something exclusive or 0 is still something. Yeah, we have it on the other slide here. And what is also very useful is that there is no replay protection. So we simply have to find one valid key release packet and modify this in an arbitrary way. So we have the replay attack possibility. We can do this known plain text attack. And what we do next is we do some simple math, namely exclusive OR, and then we can manipulate this key release packet arbitrarily and inject whatever keys we want. We also found out that the Cherry keyboard and also Perix and Logitech are using the default USB HIT human interface device data formats. So we have 8 bytes, at least in the case of Cherry. We have some modifiers, null byte and 6 key codes. And here are some examples of valid values for these data fields. And here's just a simple example. So we have an encrypted release packet. We have an exclusive OR with our plaintext packet we are forging. In this case, it's Shift plus A, so we want a capital A. And the injection packet you can see below. And that is all you have to do to have packet injection on encrypted wireless desktop sets. Yeah, and here keystroke injection in 5 easy steps. You just have to find the target device using a radio. You have to find a key release packet. This is also a heuristic. But the last packet somebody has pressed after a longer pause, for example, 2 or 3 seconds, actually is a key release packet. So you can find these packets with high reliability. You do some simple math, and then you can send modified key release packets as you want and repeat it as often as you want. And what you gain is remote code execution, as we've seen on target systems that are actually operated with vulnerable devices. Here's an excerpt of the demo code of the demo tool you've seen before. It's just a few lines of Python. It's just an exclusive OR, actually. Yeah, that's another device we've built because my boss wanted to have a standalone device. So yeah, we had an old Raspberry Pi lying around, developed a small Raspberry Pi shield, and put a radio in there, and you can do the attack also with this. Yeah, it's just a schematic. You should not take such a device in an airplane because airport security, they have some questions. So my boss did last week, and he told me not to put it in the hand luggage. Yeah. Okay, and here's some manufacturer statements and feedback, so no response from Perix at all. Microsoft, they're still checking some of the issues, actually, but some of the problems they just cannot fix, or not in the products that are already out there. Concerning the mouse communication, they said it is by design, so no fix for this. Concerning the physical access, they say, if you have physical access, you can do anything. That's actually true. Concerning not keystroke injection, replay attack, they're still working on this one. Logitech just said, thank you very much, and we're working on better products in the future. Fujitsu, they told us that these kind of replay attacks are actually hard to reproduce and you need special knowledge and stuff like that. But they're also, they will not fix this, but in future products they will try to do it better. And Cherry, they just relabeled their product. It was called Unlimited AES, and now they just don't promote it as a secure wireless desktop set anymore, and they will also not fix these issues in their product. They're still selling. Okay, so the conclusion is that all the tested devices had one or more security issues. In my opinion, you can exploit all of them in real-world attack scenarios. The found security issues cannot or will not be fixed. So vulnerable devices will stay vulnerable in the future. It's just a short summary. Here another summary. So what have we found concerning the 5 wireless desktop sets? Different vulnerabilities here. And yeah, the single recommendation is do not use wireless desktop sets with known security vulnerabilities in security-related environments. Okay, here's some references, and thank you very much for your attention. And I think we don't have time for questions.
All right, thank you, Matthias.